Our speaker today is Craig Larson from Virginia Commonwealth University and University of Montana, and he will speak on old and new results on alpha critical graphs. Craig, the floor is yours. Thank you.
Thanks, Sandra. Thanks for the invitation. Thanks, everybody, for your interest. Mark is at the University of Montana. So the talk is all about independent sets and graphs. So if you look at the Peterson graph here, the green vertices don't have any edges between them. They're pairwise, non-adjacent. They're an independent set. Finding a largest independent set in a graph is an NP hard problem. It's the complement version, finding a largest clique, is one of Karp's original 12 problems. Throughout the talk, we're going to use alpha as our notation for the cardinality of a largest independent set. So what I've done on these slides is I'm worried that they're too chock full of definitions, and I have a bad memory. So often in a talk, I've forgotten the key definitions by the time that I needed them. So I've cut and pasted important definitions to appear over and over and over on slides. And maybe it makes my slides too cluttered. It's an experiment. In the Peterson graph here, those 4 green vertices, that's the largest independent set you can find. So here our alpha is 4. Now, if you want to compute the independence number of a large graph, maybe a large random graph, that's impossible because of the difficulty of the problem. So it's one motivation for developing more theory related to the independent structure of a graph. And the things that people do are improvements on algorithms, finding classes of graphs where you can find a largest independent set efficiently. One thing people do is find bounds for the independence number. There's maybe hundreds of papers on bounds for independence numbers of graphs, or other investigations of structure. And that's what we'll talk about today, a structural investigation. So a graph is alpha critical if you remove any edge and the independence number increases, the independence number goes up. So the graph on the left is K4, and if you remove the edge 0, 1, you'll have the vertices 0 and 1 will be a largest independent set. So you'll have independence number 2. And if you could see that if you remove any of the edges of this K4, the independence number will become 2, so 1 bigger. The graph on the right is a cycle on 5 vertices. Its independence number is 2. So if you look at the vertices, say 1 and 4, that's a largest independent set. If you remove any edge, say the edge 0, 1, the independence number will become 3. So if you remove 0, 1, the vertices 0, 1, and 3 will now be a largest independent set. So these are classic examples of alpha critical graphs. Any complete graph with at least 2 vertices is alpha critical. Any odd cycle is alpha critical. And I've gone the wrong direction on my slides. All right, so the investigation of criticality in graphs, I believe, goes back to G.A. Dirac. That's Dirac on the far left. He's the stepson of the physicist Paul Dirac. He was born in Hungary, but spent the rest of his career mostly outside of Hungary. And the rest of these guys are all Hungarians. So Hungarians play a big role in this, in the criticality story in general. Arose plays a role too. Theorems of the other 3 here will show up later in the talk. Heinel was at Rutgers, and you may have even had him in your seminar. and Galai, this third person, was actually a student of Koenig, who wrote the first graph theory book in 1936 and was the advisor of Lovász. And the guy on the right is András Faj. His name is maybe less familiar, but he was at the same university as Lovász in Hungary and just died this year. So a lot of the results that I'm going to mention are recorded in this nice book by Lovász called Combinatorial Problems and Exercises. By the way, I'm in full screen mode. If you put a question in the chat, somehow I don't have chat, so you'll have to just blurt it out, which is okay with me. When I teach, I also like lots of noise in the room. All right, so throughout the talk, you're going to see references to this book because all of the old results I'm going to talk about are actually recorded in this book of Lovász. All right, so here's an important thing. So there's lots of known examples of alpha critical graphs. There's a lot of investigation of creating new alpha critical graphs from existing alpha critical graphs, so constructions. But it turns out if you take any graph, if it's not alpha critical, you can find an alpha critical subgraph. So if it's not alpha critical, that means there's some edge that you could remove, like 0, 2 here, so that the independence number stays the same. If you remove 0, 2, edge 0, 2, the independence number will still be 2. So you can take any graph and iteratively keep removing edges until all of the remaining edges have the property where removing them increases the independence number. So every graph has an alpha critical subgraph with the same independence number. All right, and the significance or one use of alpha critical graphs is investigating structural problems related to independence number. So for instance, one of the better known unsolved problems in graph theory is Hadwiger's conjecture. And one attack on Hadwiger's conjecture has been on graphs where the independence number is 2. And in a well-cited paper by Toft and Plummer and Stibitz investigates alpha critical graphs towards the goal of investigating Hadwiger's conjecture. So alpha critical graphs might have more structure than random graphs, than a generic graph. So you can, in a sense, impose some structure. All right, the most basic result about alpha critical graphs is this. If you want a largest independent, if you have an alpha critical graph and you have any edge like 0, 1 in this example, the graph that you get, its maximum independent set is going to have to have both vertices 0 and 1. And the reason is an independent set that didn't have both vertices 0 and 1 would have been an independent set in the original graph. So if you're gonna have an independent set which is bigger, it's gonna have to have both of those endpoints. So I have Lovász CP and E problems. So this is one of the many results recorded in this book of Lovász. And a corollary is that if you have an alpha critical graph and you take any edge, say 0, 1, well, 0 then is going to have to be in some maximum independent set of the original graph. So the reason is if you remove the edge 0, 1, you get independent set in the new graph with 0 and 1, well, then the independent set where you take away 1 will be an independent set in the original graph. All right. So a deeper result is a result from the 60s by Beinecke, Harari, and Plummer that says in an alpha critical graph, any two incident edges are going to be in a chordless odd cycle. That's a starred problem in the Lettelbos book. So if you look at, say, the edges 0, 1, and 0, 3 in this complete graph, they're in the chordless odd cycle, which is this triangle 0, 1, 3. But that's true even for large alpha critical graphs. The incident edges are in chordless odd cycles. All right, so the first result is going to be about twins, and they're going to be useful to us later in this story. If we look at our original C5 with top vertex 0, it's going to have some property that I'll talk about soon enough, but I might want to add this green vertex, which is going to be a twin of 0. So the new vertex will be 5. I'll make it adjacent to its twin, and I'll add all of the neighbors that were neighbors of 0. So 0 has neighbors 1 and 4. 5, I'm going to give it neighbors 1 and 4. The word twins aren't always consistent in the literature. Sometimes it's not required that the twins themselves be adjacent, but will require that twins be adjacent. Another interesting thing is if you look at papers on alpha critical graphs, once you have your eyes open for twins, all of a sudden you'll see that a lot of the graphs in these papers are graphs that do have twins. It's kind of like your kid is interested in purple cars. Well, you think you don't see purple cars, but all of a sudden purple cars show up everywhere you look. All right. The first useful theorem is going to be if you have a graph with twins, say 0 and 5 here, that graph is going to be alpha critical if and only if the graph that you get by removing the twin, so you remove the 5, is alpha critical. This theorem parallels a theorem of Lovász. Lovász proved in investigating perfect graphs that if you have a graph with twins, that graph is perfect if and only if the graph that you get by removing the twin is perfect. Turns out to be useful. All right. We'll need the matching number in the story that I'm telling you today. A matching is similar to an independent set of vertices. So we've got a set of edges which are pairwise non-incident. So the edge 0, 5, all the red edges none of the red edges are touching each other. So that's an independent set of edges. And the matching number is going to be the cardinality of a largest set of edges which are pairwise non-incident. And we'll use new. So here in the Peterson graph, the matching number is 5. The new is going to be 5. And it's also important that there's an efficient algorithm. So it looks very similar to the independence number problem. The independence number problem is algorithmically hard, whereas the matching number, similar looking matching number problem is algorithmically easy. It's non-trivial, but it's efficient. There's an efficient algorithm. All right, now here's one connection between these concepts, between these numbers, these invariants we're talking about. The graph theorists know the Konig-Egervary theorem, which says or one equivalent of it says that for a bipartite graph, the independence number plus the matching number is equal to the number of vertices. There's other graphs that have this property. So for instance, for this PAW, the set 1, 3 is the largest independent set. So the independence number is 2. The edges 1, 2, and 0, 3 are largest matching. So the matching number is 2. And here we have 2 plus 2 is equal to the number of vertices. And we have an odd cycle. So that graph isn't bipartite. So we have a non-bipartite graph that has this property that the independence number plus the matching number is equal to the number of vertices. And Deming and Sturble in independent papers of 1979 show that the graphs that have this property can be identified efficiently. And a consequence of this is if you have a graph that's Konig-Egervary, or KE, I'll start saying for short, because the matching number can be computed efficiently, that says the independence number can be computed efficiently for these graphs. It turns out that Deming provides an algorithm that actually produces the largest independent sets, which we'll talk about. All right. A word that maybe you don't see very often, but shows up, for instance, in the integer programming literature and in Lovaas and Plummer's book on matching theory, is 2-bicritical. A graph is 2-bicritical if for every non-empty set of vertices, so say the 2 non-empty independent set of vertices, so singleton 2 is an independent set, it's got neighbors 1 and 3, so it has more neighbors. The independent set 2 and 0 has neighbors 1 and 3 and 4, so it has more neighbors. So this graph is 2-bicritical. Every non-empty independent set has more neighbors. And it turns out it's a result of polyblank that almost every graph is 2-bicritical. So while you might not see this term regularly, almost every graph that exists has this property. All right, so a theorem that we'll need is a 10-year-old theorem that says that any graph can be decomposed uniquely into 2 parts, one of which is KE and possibly empty, and one of which is 2-bicritical, also possibly empty. So if you look at the orange graph here, it's almost complete except for this missing edge. So the independence number of the orange graph is 2. Its matching number is 2. You can find a matching with 2 edges. And the independence number plus the matching number sums up to the number of orange vertices. The green subgraph is 2-bicritical. Its only independent sets are singletons, and each singleton has more neighbors. And a neat thing about this decomposition is that you can prove that the independence numbers of the pieces sum up to the independence number of the parent graph. So I can find a largest independent set here with 2 vertices from the orange subgraph, 1 vertex from the green subgraph, and the independence number of the whole graph is 3. So since most graphs are 2-bicritical, in fact, most graphs don't have this orange piece, so to speak. All right, but some do. In fact, a lot of small graphs do. A new theorem about alpha critical graphs says this: if you have a connected alpha critical graph, there's no way that you can divide it into non-trivial pieces where the independence numbers sum up, like in the last theorem. And the reason I've written out details for anybody that wants to see the slides later. The details will be there. But the reason is if your graph is connected and alpha critical, and you have two non-empty sets of vertices, well, there's got to be some edge between those sets because the graph is connected. If you remove a connecting edge and you look at the largest independent set in the first piece, well, that's got to be the independence number of that piece. And if you look at a largest independent set of the other non-empty piece, it's going to be largest. It's got to be the cardinality of that set has to be the independence number of that piece. But if your graph was alpha critical, what that means is if you remove that edge, it should have increased the independence number. But you can't have both additivity and increasing the independence number here. There's no way for these cardinalities to go up. That's what the proof says. All right, now here's one of these wordy slides. In fact, the slide has two things that I already mentioned for your reference. The corollary uses both of the results. So the corollary says that if you have an alpha critical graph, it's got to be one of these two kinds. It's got to be KE or it's got to be 2 bicritical. Well, the reason is we know two things. Any graph can be broken up into two pieces, a KE piece and a 2 bicritical piece that have the independence additivity property. But the second theorem says alpha critical graphs can't have a non-trivial independence additivity. So together, that gives you, well, if your graph is connected and alpha critical, it's got to be one kind or the other. So it's got to be this generalization of bipartite graphs, or it's got to have this property that most graphs have. Non-empty independent sets have more neighbors. All right. The new thing starts with the Lovász problem. He asks in his book, which bipartite graphs are alpha critical? Well, we can generalize that question. Bipartite graphs are a kind of KE graph. So we could ask, which KE graphs are alpha critical? Now, KE graphs, Konig-Egervary graphs have the property that if you find a maximum matching, any remaining vertices have to be an independent set. There can't be any edges, otherwise you could increase your matching. And KE graphs also have the property that a largest independent set, you could take one vertex from each of your matching edges. So you could take the leftover vertices, and then a largest independent set has to have one from each of the matching edges. And the significance of this is, if you have a KE graph, you could decompose it into one piece for each matching edge, one piece for the leftover vertices, and you'd have the independence numbers of the pieces would be one for each of the matching edge pieces, and however many leftover vertices you have for the leftover vertex piece, and you do have independent summability for KE graphs where there's more than 2 vertices. You're going to have more than one piece. But we know that alpha critical graphs don't have independent summability. So your KE piece can't have more than 2 vertices. So you immediately get, if you have an alpha critical graph, a consequence of this last theorem that we talked through, an alpha critical graph that's KE can't have more than two vertices. It's got to be the complete graph on one vertex or the complete graph on two vertices. So, so this, and then you can say a little bit more than our last theorem. It says this: if you have a connected alpha critical graph, it's either got to be K1, K2, or it's got to be two bicritical. So essentially, connected alpha critical graphs are two bicritical with these two teeny exceptions. All right. The new thing on this slide is a corollary at the bottom. One of the Lovász problems is characterize the alpha critical graphs where for any non-empty independent set, the cardinality of the neighbor set is at least as big as the cardinality of the independent set. Well, now we know that there's only three cases to consider. Either your connected alpha critical graph is a K1, well, that's just an isolated vertex, or it's a K2, well, the independence number is 1, and any largest independent set has one neighbor, so it satisfies this Lovász condition, or your graph is two bicritical. And the definition of two bicritical is that every non-empty independent set has more neighbors. So that's this condition without equality. So from this way into the investigation, you get answers to these Lovász questions almost for free. All right, here's another one. Lovász asks, show any alpha critical graph with no isolated vertices has at least 2 times alpha vertices. Well, now we know connected alpha critical graphs are either K1, K2, or two bicritical. K1 has isolated vertices. K2, independence number is 1 and it has 2 times 1 vertices. The only other case is two bicritical graphs. Take a largest independent set. The condition says that it has more neighbors. Well, then the independence number has to be, so the independence number is going to have less vertices, so it's going to have less than n over 2. The independence number will be no more than, well, it'll actually be less than n over 2 for two bicritical. All right. The answer to the next problem seems kind of small. It's small when you come at it through this direction where we've developed this machinery. Lovász told me that's actually a consequence of a result of Heinel. It says this: the problem is characterize the connected alpha critical graphs where the number of vertices is equal to 2 times alpha, and we have that result now. The only possibility is K2. All right, so now I want to go back to Deming's work, an algorithm that Deming developed in his investigation of Konig-Egervary graphs, an extension that Mark and I developed, and a different decomposition of graphs into pieces that will connect up to an investigation of the structure of alpha critical graphs. So Deming in his 1979 paper, he's got an algorithm for identifying Konig-Egervary graphs. But the algorithm requires as an input that the graph has a perfect matching. So a matching that saturates all of the vertices of the graph. And at first glance, that seems special. That, well, it's not useful for determining if any graph is Konig-Egervary, but just these special graphs, graphs with perfect matchings. But Deming argues that this is actually enough. If you take a graph that doesn't have a perfect matching, say this cycle on 5 vertices, and you look at a maximum matching, say the edge is 1, 2, and the edge 3, 4, if it's not perfect, there's going to be leftover vertices. So here the vertex 0 would be leftover. Deming says, for any of the leftover vertices, vertices unsaturated by the maximum matching, make a twin. You can add, so when you make the twin, you add the new edge between the unsaturated vertex and the twin that you created, and you can add that edge to your matching. Now all of the previously unsaturated vertices will be matched. So now you have a graph with a perfect matching. And from the point of view of independence theory, or the investigation of the independent structure of the graph, this is good enough. And the reason is when you add the twin, the independence number of your graph doesn't change. So any maximum independent set from the original graph will still be, you can argue, a maximum independent set in the new graph. Any maximum independent set in the new graph that contains the twin, you can argue, well, you could have switched your twin and the vertex that it's twinning. So independence number doesn't increase. So you can always assume, for Deming's purposes, that your graph has a perfect matching. We'll call these Deming extensions. This C5 only had one maximum matching unsaturated vertex, but maybe you'll have a bunch. You twin them all, and you'll have a new graph with the required properties. So this slide just says all of the things that I said out loud. So independence number, the Deming extension will have the same independence number. The matching number indeed increases, but we know exactly how much it increases. Every unsaturated vertex is twinned. So the matching number of the Deming extension will be the original matching number plus how many vertices you had left over. And independence number investigations can mostly be done here. So for the purposes of KE theory, it turns out that these two graphs, which are not KE, are kind of the most important graphs. So that for the K4, the independence number is 1. You can find a matching with 2 edges. Independence number plus matching number doesn't sum up to 4, so it's not KE. For the graph on the right, which we call T in our paper, T for triangles, you can have one vertex from each of the 2 triangles, and that's the best you could do. The independence number is 2. You can find a matching with the edge on the far right, the edge on the middle, and the edge on the far left. So the matching number is 3, but 2 plus 3 doesn't equal 6, the number of vertices. So these 2 graphs are not KE. It turns out, you can argue that even subdivisions of these 2 graphs are also not KE. When you take an edge like the top edge and you add an even number of subdividing vertices, so here we've added 2 subdividing vertices, what happens is the independence number will go up by 1, the matching number will go up by 1, the number of vertices will go up by 2. 1 plus 1 is 2, that's balanced. But the original graph was unbalanced. The original graph didn't have this property. Subdividing the edges won't achieve the property. Your new graph is still not going to be KE. Deming's algorithm is actually going to be looking for even subdivisions of K4 and this T graph. All right. So here's what Deming's algorithm actually produces. If you have a graph with a perfect matching, Deming's algorithm is going to do one of three things. It's either going to find an independent set with n over 2 vertices. In that case, your graph will be KE, or it's going to find a subgraph which has a spanning even subdivision of K4. So one of those even subdivisions of K4 with maybe extra edges, or it's going to find a spanning even subdivision of this T graph with possibly extra edges. Adding the extra edges can't ever change the fact that your graph isn't KE. So you're still not going to achieve independence number plus matching number is equal to the number of vertices. So that's what Deming's algorithm does. And it's summarized in this theorem from Lovaas and Plummer's matching theory book, which says this: a graph with a perfect matching is KE if and only if. So a nice subgraph is going to be a subgraph where the any extra vertices, any vertices that aren't in the subgraph, any extra vertices can be matched, perfectly matched, have a perfect match. A graph is KE if and only if it doesn't have a subgraph which is has a spanning even subdivision of K4, like on the left. So an even subdivision of K4 with maybe extra edges, or a spanning even subdivision of this T graph. So the T graph with maybe extra edges. So those are obstructions. If you don't have those obstructions, your graph will be KE. All right. Now, in previous research, we weren't originally investigating alpha criticality, but you'll see that there are some neat connections. What Mark and I were trying to do was to find a subdivision of an arbitrary graph that had some nice structure. If a graph is KE, well, then we know what the independence number is. We can identify these efficiently. Not every graph is KE. Deming's algorithm says if your graph isn't KE, you'll find one of these obstructions. The obstructions, what we noticed is some of the obstructions were almost KE. Some of the obstructions were, in a sense, one edge away from being KE. So teetering on the balance of being a super nice graph with respect to independence number theory. So this is what we finally came up with. We so here's one of these. This graph right here is one of these obstructions that might show up when you apply Deming's algorithm. The red edges are all edges that are in some perfect matching of this obstruction, but they have the further property that if you remove any of those red edges and the endpoints of that edge, you'll get a new graph which is actually KE. So if you remove vertices 0 and 4 and that edge, you'll get the graph induced on 1, 5, 2, and 3, which has independence number 2, matching number 2, and 2 plus 2 is equal to 4. It is KE. This graph in fact has the property that if you remove any edge that's in a maximum matching, the result and its endpoints, the resulting graph is KE. So this graph is in this sense almost KE. So this is what we were looking for. And it turns out that these graphs that have this property, so we're going to call these Deming K4 graphs, because the remainder of the talk, these graphs can be alpha critical. We know, for instance, K4 is alpha critical, even subdivisions of K4 are alpha critical. So some of these Deming K4 graphs can be alpha critical. We did the same thing for these T subgraph obstructions, where the spanning even subdivision of T comes out of Deming's algorithm. It's an important fact for this investigation of alpha criticality that these subgraphs can't be alpha critical. The reason is this middle edge, or middle edges from an even subdivision. If you remove the middle edge, the independence number won't go up. So that's what you need for alpha critical graphs. So we call these subgraphs which are spanning even subdivisions of T, Deming BP graphs, where the BP comes from blossom pair. So they won't show up in there's an open question at the end that I'll tell you more about. Maybe they can show up. I don't know the whole story. All right. So there's a lot of words on this slide, but all it says is this: Deming's algorithm produces a largest independent set in a KE graph, or one of these two kinds of obstructions. What Mark and I did is, in the case where you get one of those obstructions, it won't be KE, and it won't necessarily be almost KE in the sense that I mentioned, but you can dig deeper. So that's what we do. If you get one of these obstructions, you can efficiently identify any of the edges that's in a perfect matching, and you can test whether removing this edge and its endpoints gives you a KE graph. So you can reapply the Deming algorithm. So either you get a Deming K4 graph, a Deming BP graph, or you can remove one of these edges. Your graph isn't KE, and you can reapply Deming's algorithm. So all we do is, in a sense, keep reapplying Deming's algorithm until you get to smaller and smaller obstructions. And the smallest obstructions are these almost KE subgraphs. And because they're almost KE, they all have the property that the independence number is one less than the matching number. So there's where the almost KE is recorded quantitatively. So they're off by being KE by one, in a sense. KE graphs with perfect matchings have equal independence number and matching number. So here's all this slide says: by this way of reapplying Deming's algorithm repeatedly, you can efficiently decompose a graph into pieces, which are these T subgraphs, which are almost KE, K4 subgraphs, which are almost KE, or a piece which might actually be a KE graph, or if the initial graph was KE, the whole thing will be the initial graph, and the vertices will partition your original set of vertices. And so here's an example. So here's an input graph G with a perfect matching. Our algorithm does decompose this graph into pieces. The edge 10, 11, that's the top edge of the input graph. The next piece, the two triangles, that's right here. So you get that subgraph, which is almost KE. The K4 is the bottom four vertices, and the pieces might have other edges between them. So you get pieces What's left out are what we call crossing edges. So you get this decomposition, and it has nice properties that are recorded in the theorem that we won't need for the rest of the talk, but it just says that the pieces are either KE, where the independence number equals the matching number, or they're one of these two kinds of Deming subgraphs where the independence number is one less than the matching number. And it also says that the matching number of the pieces adds up to the matching number of the parent graph. All right, so here's something new. The theorem says a Deming K4 graph is an even subdivision of K4 if and only if for every edge, what you get by removing that edge is KE. Well, we know that Deming K4 graphs have spanning even subdivisions of K4. And what this theorem says is, if you have any other edges, removing any of those other edges won't make your graph KE. So the only time that it's the case where you have a Deming K4 graph and removing edges makes your graph KE is exactly the case where you have an even subdivision of K4. So nothing else left. And then you immediately get that if you have one of these Deming K4 graphs, one of these graphs that will pop up in a decomposition of an arbitrary graph, it's only going to be alpha critical if and only if that piece didn't have any of these other crossing edges. But we kind of have an intuition of that. If you have a spanning even subdivision of K4 and you have other edges besides the even subdivision of K4 edges, or removing those edges aren't going to increase your independence number. So the only time that these pieces will be alpha critical is in this special case. I see that we're out of time, but we're almost done. Here's actually the last contentful slide. So the low-VOS problem is characterize the graphs where the number of vertices is equal to 2 plus 2 times the independence number. Well, you can argue that if your graph is connected and has this property, that your graph is going to have a perfect matching. From the previous theory, you can argue that your graph is 2 bicritical. It's a theorem from Lovaas and Plummer's matching theory book that if you have a 2 bicritical graph, you can cover the vertices with a matching and some number of odd cycles. And then you can leverage that fact to actually argue that this covering will just be a matching, that it won't have any odd cycles. So you'll have a perfect matching. And now that you know that your connected alpha critical graph where the number of vertices minus 2 times the independence number is 2, you can argue, and you know that it has a perfect matching, you can argue it's got to be small. A Deming decomposition can only have one piece. That piece has to be a Deming K4 graph. And you can argue being alpha critical is going to require that piece, that Deming K4 subgraph, is actually an even subdivision of K4, like here. So from this structural theory that we're developing, you can get some known results, let's say cheaply. Here's a question that I'll leave you with. Here's what we don't know. Here's something that we're interested in, is trying to figure out the relationship of alpha critical graphs from this structure theory. We don't we know that these T graphs can't be alpha critical, I believe. Here's the simplest question that I have. If you have an alpha critical graph and you take one of these Deming's decompositions of your graph, I don't think it can have any of these T subgraphs. But I can't argue it. I don't know the truth. That's the simplest open question that I've got. And that's what I wanted to tell you about. Thanks for your interest.
Let's thank the speaker. And let's, questions, anybody? And maybe I'll turn the recording off and then we can talk freely.
Talk freely?